All right, Peter is going to speak in a minute, and it's on the fly, so bear with him. This is not his usual method. Not too much time for introductions. So Peter Linderman, here's the mic.
On the fly, yes. Thanks, Rick, for inviting me to speak this morning. Can everybody hear this? Yes. Okay. Yeah, yesterday when I dropped in, I was talking to Gary, and he was asking me if I had anything I could say to the group, and I said, well, there's this thing I keep having to tell over and over and over and over and over on the phone, and it's basically the real reason why all these chargers and all these technologies really work, and it has everything to do with the batteries. And so I said, well, you know, I could sure talk about that easy. So that's how this talk evolved. So today I would like to talk to you about the chemistry, the electrochemistry of the lead-acid battery in particular, but it has analogs in all different battery chemistries. Okay, so basically our very simple lead-acid batteries, all these things that are powering these machines. Okay, basically the chemistry is that the positive plate is made from lead oxide, the negative plate is made from lead, and both of these are sitting in a water solution that has sulfuric acid in it, H2SO4. Now this all seems fairly simple. When we're running these things, when we attach some external device between these things, electricity pours out of it, and if the battery's in good shape chemically, then a great deal of electricity can pour out of it. The resistance between these two plates inside the electrolyte is as low as 1 or 2 thousandths of an ohm, and that's why the device is capable of producing tremendous currents, especially when you get into batteries this size and some of the even larger batteries. The internal resistance is even lower. And so it's that low resistance that allows the battery to produce such high currents. Now, the simplicity of this is really quite remarkable. The formulas, there are 3 formulas over here, and they describe, for all intents and purposes, all of the chemical reactions that occur in the battery. And so what I want to do is just go through these one by one and explain to you the simplicity of this. So what's happening is that the H2SO4 has actually dissolved in the water, and it's an ionic solution. And what that means is that this H2SO4 is actually existing as a series of protons, which are hydrogen ions that are missing an electron, and the SO4 ions, which have a -2 charge. And so they're in an ionic solution, and that's what makes the electrolyte such an excellent electrical conductor. Okay, because water all by itself, very marginal electrical conductor. So the whole point of having the acid in here is to create an electrical conductivity. But also the process needs a few other little interesting characteristics which the acid also provides. And we'll talk about that shortly. But the reaction is that the SO4 ion will combine with the lead, and the H2 will combine with the oxygen. So what's happening is that the positive plate here is the chemical, what we'll call the sacrificial lamb here. This is what we're tearing apart. We're chemically tearing apart the positive plate. And so what happens is the oxygen connects with the hydrogen, and the lead connects with the sulfate, and so we get this reaction. We get lead sulfate plus water plus an extra oxygen. Okay? Now, when the sulfuric acid attacks the negative plate, get a slightly different reaction. And that's described as number 2. Okay? Here again, the sulfate ion combines with the lead, and now we are left with hydrogen. So when the electrolyte attacks the negative plate, we get lead sulfate and hydrogen. Okay? And this is why it's possible to off-gas hydrogen and these types of things, which we've all seen. So when we combine these two reactions, what we get is we have lead oxide plus lead plus sulfuric acid, and we get two reaction byproducts. One is, of course, now we have a lead sulfate from this one and a lead sulfate from this one, so now we have two lead sulfates. And by the way, what that means is that lead sulfate is plating out on the positive plate and lead sulfate is plating out on the negative plate. That's not obvious in the formula, but that's physically what's happening. And because we have one molecule of water here and one oxygen and another H2O here, we end up with two molecules of water. So that is the reaction when we simply connect these two things together through some sort of external circuit. That's what happens chemically inside the cell. Now, when you read all of the documents from the early 1900s through this, by the way, this chemistry was figured out in the 1860s. And they've been studying this a very long time. When I was working with John during 2004 and 2005, we started seriously looking at this chemistry because everywhere we looked, everybody said, the answer to the question is, where does the electricity come from? And all the books and all the experts and everybody we could find just said, I don't know. Literally. Everybody says they don't know why it works. So we looked at each other and we said, well, this is ridiculous. And so John and I figured out why it works. Okay, so this is a simple diagram of what's called an alkaline fuel cell. And this is the kind of stuff that they've been using in the space program for a long time. They can take bottled oxygen gas and bottled hydrogen gas up into the shuttle and the space station and all this kind of stuff. And what they do is they react these two things. They react the oxygen gas and the hydrogen gas, and through this cute little arrangement. And what they end up with is they end up making water and electricity. Everybody knows this. This is not rocket science. Ha ha ha. So, the fact is that's exactly what your lead acid battery is doing too. The formula says that when we take electricity out of it, it's making water molecules. That is why it produces electricity. All the rest of it is just the H2SO4 is just the hydrogen donator, and the lead oxide is the oxygen donator, and that's it. It's been sitting in front of everybody for 150 years. And why they continue to refuse to believe what the formula says and everything else, well, never mind. So once John and I figured out that the stupid thing is just a water fuel cell, we said, why do these things ever break down? Why can't you charge it and discharge it 1 billion times? And there really isn't a reason. There isn't a chemical reason. Now, there are real-world reasons, and we'll get into those. But the chemistry does not prohibit the idea that these devices right here on the table, here, that the manufacturer and everybody says you can charge them and discharge them 100 times, 600 times, something like that. Getting 5,000, 10,000, 15,000 cycles out of these things is not impossible. Buying a battery, charging it, and discharging it once a day, and getting 5,000 cycles out of it, that means the battery's working perfectly for 15 years. It changes the economics of independent solar power and things like that. Most solar installations are replacing their batteries every 3 or 4 years. Golf courses are changing the batteries in their golf carts every 3 to 4 years. This has nothing to do with the defect in the chemistry. It has everything to do with a defect in how the devices are charged. So, what I want to do is I want to go through the process of what happens during a discharge and what happens during a charge. So most of us know that when you connect the battery to a load, the voltage will drop, and then it will sustain for a while, and then it will start dropping off. We've not only seen these charts, we've seen this behavior in the battery. And so what I want to do is I want to describe to you the chemistry of what we're seeing here. So this is the voltage, and this is the number of hours it's operating. And so this has within it a specific discharge rate of amps over hours. Okay. So what's happening is this. We can see that the plateau of this discharge is right around 2 volts, and this is the typical behavior of a lead acid battery. Before they started naming things after people, in other words, They had very much more interesting names for these electrical properties. And so if you read Tesla and everything, I don't think he rarely uses, back in the 1800s, he's not using words like volts and amps. He's using terms like potential or pressure, things like this, okay? So this 2 volts represents what we'll call the electrical potential difference between the plates. And it is also represented by the actual chemical difference between the plates. In other words, one plate is lead oxide, one plate is lead, and it's literally the difference, the electrical difference between those 2 substances when they're sitting in sulfuric acid that is this electrical potential. Now, we saw that as the battery discharges, we saw the chemistry. As the battery discharges, 2 things are happening. Sulfate ions are plating out on both plates, both the positive plate and the negative plate. And water molecules are being added to the electrolyte. So what's happening? What's happening is the difference, the chemical difference between the plates is disappearing. The plates are beginning to start looking more the same. They're both looking more like a layer of sulfate, lead sulfate, instead of looking like lead oxide and lead. So as you discharge the battery, the chemical difference starts degrading. And that is the voltage drop. That's why when the battery is discharged, it can't develop the voltage, because they're not different. When the battery discharges, it can't produce current, because we've just taken 7.5 hours of watering down the electrolyte. There aren't any ions left in solution to conduct the electricity through the electrolyte. And so it stops being able to produce current. This is as easy as baking muffins. This is like simple to understand. Okay? So the discharge process is just really easy to see, really simple to understand. And so the condition of the discharged battery is also simple and easy to understand. The plates have lost their difference, and the electrolyte doesn't have any acid in it left. How could that thing produce electricity? It doesn't. Okay? Everybody calls these 12-volt batteries, and everybody knows there's 6 cells in them. And so the idea is that each cell produces like 2 volts. But that's not really what it is. That's just a lazy bunch of junk. Okay? It actually produces slightly more than that. And because we know that a 12-volt battery, when it's fully charged, should be resting at about 12.6 volts. Okay? That's the standard in the industry. So what it means is that each one of these cells, each individual cell in the battery, is supposed to be producing, when it's fully charged, supposed to be producing 2.1 volts. So that 6 of them together would produce 12.6. Okay? So, now this is the most important chart that you can find on battery charging. And is the key when John and I found this, we knew what the chargers had to do. Okay? So what happens is, as soon as you start, let's say the battery is discharged down at 2 volts, and so as soon as you put it on the charger, it rises, it quickly rises to the beginning of what we'll call the charge plateau, which is pretty much this area here. And so it's going to sit there, and the voltage isn't going to rise very much. It's going to rise slowly. But this is where you're really pouring the energy in and reversing these chemical processes that I talked about earlier. And then the first significant event is here, labeled O on this chart. And sometimes this this event here is even more dramatic than it shows here in this drawing. When John and I started charting batteries under charge and being able to look at charge cycle after charge cycle after charge cycle after charge cycle, this event we started calling the knee. And what happens is that you can see that probably over 3/4 of the time is on this slow, steady ramp, what we just call the charging plateau. And the voltage is rising slightly, but here the voltage starts rising much more significantly and keeps rising and rising and rising to this point. This point then is of premier significance. And right here, this little peak and then this slight notch, right here, the voltage stops rising, it drops just a little bit, and then it plateaus indefinitely. Now, this event right here is the battery telling you the chemistry is done. There isn't one ion of sulfate left on the plates. It's 100% in the electrolyte. The chemistry is done. So, at that point, anything more that you put into the battery at that point can't charge the battery anymore because the battery is 100% charged. And so what can happen if you continue to charge it here is that the machine starts running as an electrolysis cell. Starts breaking up. Don't forget, what it's doing is it's breaking up those water molecules that we made. We're putting the hydrogens back into the solution, and we're taking the oxygens and plating them back out on the positive plate. That's what chemically charging the battery looks like. But if there's no more sulfates to give up, no more sulfates to displace, what happens is that all the electricity you put into the battery at that point just is lost, 100% loss. It just off-gasses this hydrogen and oxygen. Okay? So, the idea is, if you're watching what the battery is doing, then you can see this. It just tells you. Because the voltage keeps rising and rising and rising, and then it hits its peak, and then it drops. The only thing that will make it drop here is that it's telling you it's done with, the chemistry is done. Now, what we also saw, in especially batteries that were old and not in perfect shape, we would see, as the battery voltage was rising, we would see little drops in here, for instance. We would see a little drop here. And we started watching these things. And then it would rise, 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 drop a little bit, and then continue to rise. You may have seen these things. What's happening there? What's happening is that the battery is chemically healing itself of internal layers of sulfation that have been unchallenged for a while. And what that means is that the impedance of the battery is dropping, which means that the resistance in the electrolyte is dropping, which is good. And it also means that it's more difficult for the potential difference on the plates to maintain the voltage. That's why you see that little drop. As long as you're seeing these types of things in the middle of a charge process, this is a good sign that what's going on in the battery is going to make it a better battery. Okay? So, let's go back. What I want to do, I'm just going to leave this right here. Yeah. Okay. We'll just leave the camera where it is for ease's sake here. Anyway, what's up there is just the loading process or the generator that's charging it. And so what I want to do is I want to talk about what happens when a charging process is not complete. Let me just go back and just look at this chart again, because this is very, very telling. The alternator in your car is designed to have a voltage regulator that tops the battery out at 14.7. 14 volts, 14.7 volts. Most battery chargers that you buy commercially are similarly configured so that they will let the voltage on the battery under charge rise to 14.7, and when it gets there, it says, done. Everybody's happy. Everybody except the battery. Take a look at these numbers here. And take a look, very, very good look, because the fact is that this chart says a lead-acid battery is done at 2.7 volts per cell. A little bit of quick math times 6, 16.2. The battery isn't done until the voltage reaches 16.2. That means that we're operating in an industry that has set a standard for charging batteries which is known to not finish out the chemistry. This book was printed in 1920. It's not that they don't know. It's that their business is to sell batteries. And they have to make them work with some sort of reasonable amount of time. To keep this scam going another 100 years. Okay. So, let me see. So here's what happens when we treat batteries this way. When we take the battery to 14.7 or 15 or 15.2 or whatever the charger will allow. What happens is that, yeah, you know, this becomes mostly lead oxide again, and this becomes, yeah, mostly lead. But since we didn't finish the chemistry, there's a little bit of sulfate left on the plates. Just a little bit each time. And lead sulfate is a semiconductor. It's not a very good conductor. So by the time you do this a couple hundred times, this doesn't look much like lead oxide, and this doesn't look like lead anymore. What it looks like is something that you would find in a French bakery called a croissant. Just hundreds of micro-thin layers of lead and sulfate and lead and sulfate and lead and sulfate.
So how does it get to the 14 point? If it gets to the 14.7 again, because the amount that is left should be the same all the time.
Except the other layer was buried.
Never got rid of it.
Because here's the thing. Batteries are never treated in a way that optimizes the chemistry. They're used the way we want to use them. Okay, so especially a solar system is the worst possible set of conditions because the sun doesn't come out all the time, and I want my beer cold, and all these things. So what happens is that we use batteries under a set of conditions that I describe as charge as you can and use as you must. This has nothing whatever to do with how to make the battery last. An indefinite number of charge cycles. And because, you know, the tax code and everything else keeps us focusing on other things in our lives. This little detail has been able to be kept a trade secret for an inordinate amount of time. So the trick is that once we have a battery in this condition, where it has been charged and discharged and charged and discharged and charged and discharged, but never charged all the way back to the end of the chemistry, the battery behaves extremely marginally and is usually just handed off to the recyclers. Oh, you need a new battery. This thing can't do anything. Unless you bring it to John. You know, I don't know how many hundreds of batteries that have been, you know, out in the field for years, frozen in the winter, left on the floor for 10 years, reading 0 volts, real boat anchors, with the outward appearance of a battery, have been brought through John's shop and within a ridiculously short period of time are put back into full service. Many of them having battery capacities in amp hours of above 90% of brand new, some of them 110% of brand new. All of this is possible. It's been done so many times we lost count. So the trick is that all of those layers of sulfation that are left on the plates, the process of the rejuvenators And even the other chargers that can be used to rejuvenate batteries but don't have the automatic rejuvenation cycles in it. What are they doing? Why does this work? What are these chargers doing that are different from anybody else's charger? First of all, they're taking advantage of this. The little spanker, the little 2 amp, the 2A12. You ever see where that pushes a battery? High. High. It can push it. It can push it and push it. It can push it up. You can push it to here. It's not about how big it is. That stupid little charger beats the pants off of things that, what's the deal? John found the rules of how batteries work and builds chargers that obey the rules. How tough is this? Okay, so what we found is that if you just take a battery that has all these problems, multiple layers of sulfate in the plates, and you just charge it up once, everybody thinks, oh, I don't know how to do it. It doesn't do it. There's just so much that the battery will absorb. Each one of those little layers is a semiconductor. And so it has to do with how deeply the currents and the plating processes can penetrate into the plate. If you notice what the rejuvenator machine does, it charges and then discharges. Then it charges again and then discharges a little deeper. Charges again to the top of the chemistry. Every time the rejuvenator charges, it charges to here. Then it discharges it a little deeper to challenge deeper layers of sulfation. But at least it's not digging through layers of semiconductor. So then it can get deeper into the chemistry. And then charge it all the way back to the top again. And then discharge deeper. And this process of charge and discharge, charge and discharge, charge and discharge, charge and discharge, you can finally start rooting out all of the layers, no matter how deep they are in the plate. The machine is designed with a specific program that will manage this process. It will take it to a certain depth of discharge. Some batteries have been dramatically abused beyond that point even, which is why sometimes the rejuvenator doesn't quite bring the battery back. The only thing you have to do manually after that is just discharge it deeper again. And keep discharging it deeper and charging it back to the top until you've challenged every single layer of sulfation that's ever been plated out during a deep discharge. When you're done, you have chemically rebuilt the battery. The positive plate is 100% lead oxide. The negative plate is 100% lead. Every single sulfate ion is in the electrolyte. And you have proved to yourself that by Gadfrey, this is a water fuel cell.
What if you have a battery where somebody dumped they dumped the acid out, whatever acid you have to dump that acid out, just water or
Yeah. The question is, what happens if somebody who doesn't understand the chemistry of a battery dumps the old electrolyte out and just pours more acid in? This completely changes the balance of the ion structure in the battery. You may or may not ever be able to balance it out again. That's something that you should never, ever, 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 ever do. The only thing you should ever add to the battery is water, because the number of hydrogens and the number of sulfate ions in the battery is always in the battery. They don't go off. They don't off-gas. They don't go anywhere. If it isn't in the electrolyte, it's because it's in the plates. And you can't get the thing to work better by pouring new acid in it. It's not how it's done. These things are really important to understand. The machines that are sold here are absolutely the best battery chargers in the world. I don't have any hesitation in saying that. They treat batteries the way they're meant to be treated. Let me talk to you a little bit more about this chemistry process. When the battery is delivering current, when it's discharging, the process is very simple. The hydrogens from the H2SO4 are going over here, you can just see, going over here and attacking the oxygen on the positive to produce a water molecule. Okay? Now, that's the only electrochemical pathway that's available during discharge. Discharge is not the problem. The problem is charge. Now, when we want to reverse that, what we have to do is electrically split the water molecule, which is no problem. You put electricity into water and it splits. But if you do that and call it an electrolysis cell, what happens is the hydrogen and oxygen off-gas as gases. And if that happens in your battery, you just poured electricity into this thing and didn't charge it. We need something completely different to happen than that during charge. What we need is for these hydrogens to not off-gas as hydrogen gas. We need them to go back into solution as H+1 ions. And we need that oxygen to go back over here and chemically combine with the lead to produce lead oxide and plate out on the positive plate. We need to be able to destroy a water molecule, the one we created when the electricity was made in the first place, and do it in such a way that it causes a chemical change in the battery. And there's a lot of ways of doing this wrong. There are two primary evidences which tell you that your battery charging process is not going well for you. One of them is if you see bubbles coming up out of it. If it's off-gassing, you're just burning electricity for fun. The other thing is if the battery's heating up. If the battery's heating up, you're running it like a resistor. That's not a chemical change either. You may notice when you charge batteries with John's chargers, doesn't heat up, Doesn't off gas until right at the end. Right?
Correct.
Okay. That is what we call the cheap lab test. Okay? You don't even have to pay some engineer to tell you that this is an efficient charge method because there are no secondary waste byproducts. When John's chargers put electricity into the battery, it is converted into the chemical change that represents the actual charge. And that requires that you observe the battery. Most battery chargers don't do that. If you just pour current at the battery, the way the battery will pour current at you, the charge efficiency is extremely low. You're lucky to get 30, 35, maybe 40% of that energy back. If you meter it from the wall with a standard charger, put it in the battery, and then meter it going back out, you're really lucky to get 35, 40% efficiency. It's atrocious. Because the battery's warming up during the charge. The faster you try and do it, the worse it gets. And that's because these sulfate ions have a lot of mass. They move slowly. And to get these to move around, what you need to do is you need to raise the voltage a little bit. You need to, because these things are just moving around in here. All of the action in here is, there's no magnetism in here. This is all electrostatic pressure. Things are moving around because there's an electron displacement. Electrostatic fields are what's pushing these ions around in the solution. And electrostatic fields, electric fields, is just about potential. It's about pressure in the system. So that's why these systems work. When you discharge an inductor, creates that big voltage spike, gets that potential up. Or the other way that John's doing it is charging up a capacitor and dumping it down on it at maybe twice the voltage. But then, after you deliver that pulse, you wait. You wait until these big ions can respond to that impulse. If you don't, you're just running a resistor. If you wait, if you pump and wait, then the ions have to resolve the potential difference. And they start moving to where they want to go. Start moving to where the potential is the opposite. And this isn't just, the big buzzword out there is pulse charging. But these chargers are not just pulse charging. They do use impulses. They do use these methodologies. But in a much more sophisticated way. It's not just about, even the big pulse chargers out there will usually, especially when you get into the really big batteries, they have a thermal sensor that you stick on the battery so that when the battery gets too hot, they shut off for a little while. And they think that's really good. John's chargers never heat the battery, period. So he doesn't even need a heat sensor. He knows he's not going to heat the battery. So that's still the evidence that everybody out there is still doing it wrong. It's not charging the battery the way the battery wants to be charged. And see, if there wasn't a number of other electrochemical pathways here, then their method would work, you see. But the fact is that the way the energy comes out of the battery as just reams of current, it can just produce continuous current. Fantastic. But if you charge it that way, it destroys the battery. That is not the way the battery wants to be charged. It has to be charged with voltage pulses and waiting periods so that it has time, it has enough potential to move the big, heavy ions. So that's why these chargers are more efficient. They draw less from the wall. They get more of it into the chemistry. Now, one other thing I want to show you. And it has to do with this graph again. I'm sure many of you have noticed that John routinely builds these machines and can get them to run indefinitely on batteries. He can just turn them around and they just keep going and going and going. I've seen him run things for 6 months at a time on the same batteries. I've seen systems run, where they're just taking a battery off the back and sticking it on the front and just goes and goes and goes, monitoring it up with computers and everything else. And every single time I ever tried to do that at my house, I swore to God that I had a magic wand. Now, to be sure, there's a narrow window where this happens. But the first time we saw this elusive process was when I was working for John in 2004. We were doing the original experiments on the development of the first golf cart charger. And every single day, I would come to work at 7 o'clock, drive the golf cart charger around for 5 miles, come back in, plug it into the machine, and we would chart the charging process. And after the battery started working pretty good, we started seeing something that was absolutely unexplainable. And here's what we saw. On Monday, after the battery had been resting for 2 days without being used, on Monday, the charge looked pretty much like this. And we were happy. On Tuesday, the charge diagram got to here and went almost straight up and finished there an hour before. Wednesday, same thing. Thursday, same thing. Friday, same thing. Monday, that. Did intolerable number of charge and discharge cycles driving the thing 5 miles. Same discharge over and over and over and over and over. There was no difference. What was different was that there was something, some other energy in the battery. It was showing on the graphs. If you charged and discharged the battery in a continuous loop within a period of time, this top-out event simply happened much earlier. all this looked the same. Na, 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 zip. Done. If your batteries aren't doing that, you're not going to get them to run forever. This is the trick. The trick is that if you aren't constantly using the battery, charging it and discharging it and charging it and discharging it and charging it and discharging it within a certain time frame, you will never see this happen. If you do your tests once in a while, if you get around to it with a yawn, if you are a weekend warrior, I'm going to work on this all weekend. You're never going to see this. If you don't do it all the time. It finally just threw a pie in our face when we caught it on the computer. There it is. Drat. We have no idea why it's doing that. But it did it every time. If we waited one day, in other words, if we charged and discharged it once a day, it would top off really quick. 1 day lag, it would kind of be about there. 2 days over the weekend, there. There was something that took about 72 hours to completely dissipate in the battery. So when John, speaks all this mumbo jumbo that everybody, says, well, there's something going on in the battery. And everybody says, well, what is it, John? And he says, well, I don't know. We don't know. But it happens. And the only way to take these things, just one of these simple machines that's just doing like this, just charging and discharging back and forth on a set of batteries. If you don't go continuous, if you don't run John always says, well, just set it up and just let it run. Ever heard him say that? That's the only time you see it. Set it up and let it run. Just do it over and over and over and over and over. Just start moving those batteries from front to back, front to back, front to back. Then it starts showing up. There's no electrochemical explanation for that event that we know of. Why all of a sudden the chemistry just says, I'm done. An hour early, which means you don't have to run the charger another hour. Don't pull it, all that. There's nothing in the physics books that says, oh yeah, batteries do that when you pay enough money. So, yes?
In doing that, how far left can you go? Can you shorten the cycle and get more back?
You can't make it do anything. All you can do is watch. You can watch what it is doing. And, we were using, when we started seeing this about 72-hour window, we were using 225 amp hour batteries. This was a golf cart, 36 volt, 225 amp hour, big battery. Big battery. But once we saw that was the first system that we started actually making a graph and printing it, sticking it in a book, day after day after day after day after day after day after day. We had seen that, some machines would run, you could do this battery flipping thing. But the only times I ever saw it working was when it was run continuously. It never worked when you ran the test once in a while. So, yeah.
Is there a hypothesis about what this anomaly is caused by?
John and I have no idea what it is. You're welcome to think one up. My bet is it'll be wrong. What?
On the discharge side, did it discharge differently?
Nope. Nope, the discharge was full. In other words, when this happens, this is a chemical indicator. The chemistry is done. It doesn't go there for fun. It only goes there when the sulfate is 100% out of the plates and into the electrolyte. Yeah.
I've heard John say sometimes to let your batteries rest. Is there any reason why you want to let that weekend circumstance exist?
I don't know what the context was when John says let the battery rest. I mean, John lets the battery rest, about 80% of the time during the charge cycle. So I don't know what that means. I know that phenomena only happened if you were working the battery, charging it and discharging it on schedule. Yeah.
I also noticed that many times when I disconnect everything,
Yeah.
because I'm afraid to leave it alone, then I see that afterwards I measure the potential and it still is going up.
Yeah. We've seen a lot of that kind of thing. Depending on the method of pulse charging in some of these systems, the battery will continue to charge for up to half an hour, maybe 45 minutes after you've disconnected the charger. Yeah.
So that process maybe still continues whatever makes it happen going up. And if you let it rest for too long, I do say all this, I say it.
Yeah.
All what you just described, I say
Yeah.
it. And maybe this process that after half an hour it stops. If you let it rest for the weekend, then it doesn't start again. So
Something resolves. Right.
you know why it's still going up after half an hour?
Yeah, it has to do with the process of creating this overpotentialization on the plates. In other words, we're not just, what the industry says is, all you need to do is be 2 volts above the battery and you can just pour current on it. And we're not doing that. What we're doing is we're putting spikes on it that are anywhere from, twice the battery voltage to higher than that. And then, dropping a set number of joules onto the plates and then just disconnecting and waiting. And forcing the plates to absorb it. And this process we refer to as over-potentializing. We're literally pushing the voltage to much higher levels than it can chemically hold itself. And we believe that there's some sort of electret effect or some way that this over-potentialization is stored in the ion structure. And that it takes a while for that to dissipate. That would be our best guess. Yeah, there's things going on in these things that are not explained. I've explained the chemistry, and that's more than you'll get from almost anybody. But there's other things still going on in these batteries, there's no book written yet that describes. We can see them, we can catalog them, we can chart them, still can't explain them.
I've got some Exide batteries. They're the 2.2 volt, 1060 amp hour batteries. The cool thing about them is they're clear. You can actually physically see the plates. Now, I did observe that the one plate the batteries are about 20 years old. And I noticed that the one plate, positive plate, has all the layering and some look like little layers of paper on the edges of the plate that are falling off. However, I noticed that the negative plate looks like she's just brand new, nice and big and fat and thick, and doesn't have all the little eccentricities that the positive plate has. Now, having purchased some brand new little motorcycle batteries with the acid in the bottles, they tell you to put the acid in and then be careful with your connected right, because you can actually charge the battery backwards. Now, looking at the fact that my negative plates are 25 years old and they're nice, big, and fat, and that's what we're sacrificing,
No, you're sacrificing the positive.
Correct, but the negative plate is really big and fat and untouched.
Right.
And I thought, what about if we were to drop that right down and then charge her backwards?
You can.
Would that not be a good thing?
Well, here's the
Give
thing.
you more life?
Well, you'd have to, quote, reform the battery. See, before they figured out that you could just take, a block of, well, just originally when they figured out how to make a battery, they just put 2 lead plates in sulfuric acid. And what would happen is that the sulfuric acid would attack both plates, creating lead sulfate on both plates. And then they would, because at that point, they're the same, okay? And then they decide which one's going to be the positive and which one's going to be the negative, and then they energize it, and it starts the process of putting sulfate into the electrolyte back and then oxide on one side. Because all they're doing is they're breaking down the water molecules and starting to produce this process, okay?
How do we reform it though?
Well, the way to reform it is to go back and do forming. In other words,
Discharge it completely and then start flipping.
well, see, here's the problem. When you discharge completely, yeah, you end up with 2 plates that have a lot of sulfuric, lead sulfate on them. Yeah, then you can turn it around and see what you can do. It can be an expensive failure because you're not used to the process or how long it takes and how many cycles you may have to go back and forth charging and discharging and so on.
Can I kill the battery?
Yeah, you can make it into a big bucket of mush.
Well, that's not something that you would recommend.
Not if you
Is there a procedure?
not if you have something better to do.
All right.
Yeah, it is possible. Yeah, I mean, it's just, it's, yeah, I mean, look on the internet about battery forming. In other words, the original process of making a battery from scratch. Yeah.
Sometimes the batteries, pieces of lead fall off.
Right.
If you start charging it properly, will it dissolve that with that?
Nope, it won't. And that's another part of the scam. If you charge a battery too hard, it will force, see what's happening is, again, if you look at this, see this is a very tricky deal to get this, when you split the water, to get this oxygen to combine with this lead to make lead oxide again. Because that's the only thing that represents charge. If you aren't doing that, then you're not charging the battery. And what happens is that when this is done insufficiently so that this bond is really well established, what happens is that this material starts dropping. It may form, but if it doesn't form in such a way that it actually plates to the plate, it will fall to the bottom. And at that point, it is disconnected from the electrical circuit and becomes an inert sludge at the bottom of the bucket.
Does that harm our battery?
It can. Now, what happens is you'll notice there is a distance between the bottom and where the plates end. Okay? Now, I'm sure you've noticed when you've bought a car battery or battery for your car, you can buy a 24-month battery or a 36-month battery or a 48-month battery. And if I told you that the difference between a 36-month battery and the 48-month battery is a 1/16 of an inch down here, you'd begin to understand the price difference.
Can we ever remove that stuff from the bottom?
Yeah, sure. Yeah, the process is get it yourself in a rubber suit and open all the tops and pour all that stuff through a coffee filter. And then when that's not enough, you get out your pressure washer and you spray sulfuric acid all over everything so that there's holes in everything that you've ever worn. And you dump all that out, and then you filter your old electrolyte and pour it back in. And quite often that will get rid of the short circuits. Yes, you can. But it's a mess. And so, anyway. We're way over, right. Got to wrap it up. Okay, great. Lunch is served. Thank you very much. Appreciate it.